Sharpening drills. It doesn't have to be difficult. If you don't have a bench grinder, go get one. Lay your index finger on the tool rest, take the drill, hold it with your thumb, rest the drill against the wheel, and sweep. Keep the drill cool to avoid changes in its hardness, and if you feel confident, use the entire width of the wheel. Try to ensure it's symmetrical, and you're good to go. But the question is, does it cut? Yes, it cuts. It's not the best looking hole, but that's on me. I should have picked another drill. Do you have an idea how old this drill is? Hey, I totally get it if you tell me this was too fast or even superficial for you. So let me try to explain in a better way. Sharpening involves modifying the tip of the drill, so before anything else, it's essential to understand what a properly sharpened drill looks like. Otherwise, what are you looking to achieve during the process? And how do you know when to stop? Just to make sure we know our drills, let's go over the basics. When you go to the hardware store to pick up a drill bit for metals, you're probably buying one made out of HSS. That's high-speed steel. Compared to the drill I just sharpened, which is much older and made only of high-carbon steel, HSS drills are a lot harder. They can withstand higher temperatures without losing their temper, and they're definitely not as easy to burn. For that reason, you can run them at higher speeds, and if you treat them well, they'll stay sharp for a long time. When it comes to their finish, you might find them in several colors. It's not that they're made of a different material, they just have different coatings. While some say it's just marketing, others will defend the proper coating will make them last longer. Maybe it depends if you buy a good quality drill or a cheap one. I can't really tell you, I only have cheap drills. Titanium nitride, black oxide, John Player Special, cheap Chinese titanium aluminum nitride with silicon, also known as nano coating. And I know it's not a drill, but you get the idea. Any of these is good to drill mild and low carbon steel. For aluminum, you're better off using an uncoated drill. That's because when temperature rises, aluminum has a tendency to weld itself to cutting tools. Since coated drills have rougher surfaces, there's more friction and therefore more heat generated in the cutting process. That's why, generally speaking, the polished surface of an uncoated drill is better for aluminum. Next we have HSS CO drills. 9 out of 10 they're golden, but they don't really have to. Same deal as HSS, it's just a coating. The CO part after HSS means cobalt was added to the composition of the drill, typically 5 or 8%. That makes the alloy harder and able to withstand even higher temperatures. But by being harder, these drills become more brittle. When you break a drill like that, you're in trouble. These snap while breaking through the wall into a dovetail. Now to remove it, so when should you use a cobalt drill? When you want to drill stainless or other tougher materials, like titanium. You can also use cobalt drills for steel, just have in mind they're more expensive. On the other hand, you're probably getting more life out of them, so it's something to think about. Finally we have tungsten carbide drills. In a machine shop, you'll probably find them in the form of solid carbide drills. And these are not cheap. They're very hard, good to drill hardened steels, but again, hard means brittle. If you drop one, it will most likely break or chip. Any flexing or bending and it will snap. Also be careful with temperature shocks, aggressive feed rates or vibration. They're that easy to chip. They're actually very good drills, but they don't tolerate any abuse. For instance, forget about using a solid carbide drill in your cordless drill. You need a rigid setup. The cutting action of a drill is made by the two opposing cutting edges. These cutting edges slice the material into chips while the drill digs into the material. Chips and heat are byproducts of the drilling operation. When you buy a chip drill, it's very likely that it has a point angle of 118 degrees. That's the included angle formed between the two cutting edges, or cutting lips. This angle has been advertised over the years as a generic angle. You know, one that works for all materials. While that's not completely wrong, the fact is, the type of grind that goes with it is actually very convenient to produce. And by convenient, I mean cheap. Cheap grind on a cheaper material, for sure that's one way to make a product popular. Now if you buy a cobalt drill, or just an expensive HSS, it's almost guaranteed it'll have a different type of grind, and a different angle. 135 degrees. Take a look at this drill. It's marketed for tougher materials, like stainless. So it's not a big surprise that it comes with a more favorable angle out of the box. After all, you're paying for it. You see, in theory, there's an ideal angle for every material. But this is all to tell you that, unless you're buying something exotic, these are the 2-point angles you're going to find. For the kind of use you have in a home shop, it's unlikely that you'll find a lot of difference between the two. So I'd say, experiment a little bit and then stick to the one you like the most for all your drills. Or have 2 sets if you like. But when the sharpening time comes, replicating exactly the original angle is not very critical. What's critical is to make sure both cutting edges have the same angle. If they don't, when you start drilling, the drill will walk on the part, and also produce an oversized hole. Now to get in the ballpark of 118, you can stick 2 X-nuts together. They form an angle of 120 degrees. That's close enough to check the angle as you sharpen. And if you're not sure if you have the same angle on both sides, you can double check by measuring the length of the cutting edges. For that, you can use a simple ruler. Just make sure they measure the same. For the 135 angle, you'll have to use a protractor. But why don't we make something better while we have a minute of silence for all these drills? You can buy this type of tool for like $10 on Amazon. Just saying, it's not worth making them yourself. If you look at the profile of a twist drill, you might say it looks like a cone. In reality, it's not a cone. This is a cone. Allow me to demonstrate why drills are not ground this way. Just to state the obvious, the drill can't cut much like this, and the sound you heard was this flank rubbing against the metal. Now this happens because the cone doesn't provide any clearance behind the cutting edges. In fact, I don't even think we can call these cutting edges. A cutting edge has to be relieved. Think of a knife. The cutting end is relieved on both sides to form the cutting edge. That's what allows it to dig in when you push on it. You wouldn't have much success cutting with this side of the knife, would you? The same happens with cutting tools. All cutting edges need to be relieved so they can dig in. And in the case of a drill, the relieving of the cutting edge will, at the same time, lower this flank and stop it from rubbing. That's 7 to 15 degrees, what you're looking for, between the outer corner of the cutting edge and the hill. Rule of thumb, aim for the lesser if you're drilling harder materials and give it a little more clearance if you're cutting something soft. The reason is, small reliefs mean more material behind the cutting edge. That provides better support during the cut, and can prevent the edge from chipping or breaking. On the other hand, if you're drilling a softer material, you can have more clearance. You don't need such a strong cutting edge and can benefit from other factors like having less heat building up and evacuating chips faster. Okay, so this was all to tell you one of the most important aspects related to the sharpening of a drill. You need to relieve the flanks or your drill will rub. I don't know about you, but I have some factory sharpened drills rubbing on the hill. At first glance, you could say there's a clearance issue. And you'd not be wrong. If it rubs, there is a clearance issue. If you trace a line between the lip and the heel, it's very easy to jump to that conclusion. However, see the dip midway? Yeah, that flank is not a simple plane on an angle, but in fact, a series of compounding angles. So you can't really tell the relief angle by looking at the drill from the side. You need to look straight at the tip. This section is called the chisel point, or chisel edge. We'll come back to these, but for now let's grab a protractor and check the angle between the cutting lip and the chisel edge. 110 means there's just a small clearance ground, while closer to 135 means higher clearance. This drill seems to have 132 degrees, which in fact is high clearance. In these cases, it's enough to grind the secondary relief angle here. That'll stop the rubbing. Now if you look at the drill I just sharpened at the beginning of the video, you'll notice the angle seems quite steep. In fact, look at that. That's 118. In terms of cutting edge clearance, that's like 7 degrees or so. So this is actually a strong cutting edge for steel. Enough with the talking already. Let's sharpen some drills. I know, lots of new drills. Why would I waste time sharpening old ones? That's what I used to think until the other sizes in my cobalt set started wearing out. Buying cobalt gets expensive very quickly. I can't just throw them away and keep buying new drills. Anyway, don't get fooled by the big box. This is cheap HSS. I'm gonna take 2 drills to show you some different point styles and how you can grind them. 9.5 and 13mm. And I'll start by trying both with a factory grind, just as they came out of the box. Obviously, you can't feel it in a video, but the sound should be enough for you to spot the rubbing. I was feeling hard and could feel the drill bouncing back. Now, I'm not an expert, but I think the chips tell the same story. Looks like chatter to me. And I know there are a lot of reasons for chatter, but in this case, I believe rubbing is the primary cause. It's forcing the drill to bounce back. Yeah, it isn't just wear from the chips, it's rubbing. Let's try the 13. I'm constantly packing to break the chips because they're almost touching the camera. As for this drill, it feels a lot better than the other. So before I actually start sharpening, there's one more thing left to do, and that's dressing the grinding wheel. I really wanted to make a dressing jig, kinda like the Wolverine jig. I don't know if you're familiar with it, but since I don't even have the bench grinder bolted down yet, that's something for another day. For today, I got this cheap diamond dresser. I'm not entirely sure this is a good idea, probably not, but let's see what this can do. Yeah, I kinda was expecting this. The wheel looks nice, but now it's out of round, and much worse than it was before. And this is exactly why I want to make a fixed system to dress my wheels. Most people refer to these as the conical point, and although we've just discussed why drill points can't be conical, I don't have a better name for these. Just be aware that in this case, conical doesn't mean we're going to make a cone. So, point angle. For this type of grind, typically 118 degrees. It's the cheap type I mentioned earlier. Doesn't mean it's bad, just cheap to mass produce. To replicate it at home, you can use a bench grinder like this or a belt sander. You'll also need some container with water to dip the drill. The act of grinding is very simple. With the drill at the correct angle and the cutting edge parallel to the axis of rotation, you gently let it touch and then sweep up and roll at the same time. Sweep and roll. Sweep and roll. This movement will both sharpen the cutting edge and create the necessary relief behind it. So before we move on, let's just define correct angle. These will determine the drill point angle, so you need to be consistent when you take the drill against a stone. Don't forget you need to dip the drill every now and then, and that there's two cutting edges to grind. So repeating the same angle might be difficult at the beginning, but I assure you it's a matter of practicing. You'll get it right after a while. A small trick to get there faster is to have a visual reference. Just for simplicity, I'm using a 60 degrees angle. This angle should be half of the angle we want for the point, the included angle. You might not realize this, but when you sharpen on a bench grinder, the curvature of the grinding wheel helps taking care of the relief behind the cutting edge. Next, I'll drill a hole to compare with the factory grind, but before that, I want to explain why I'm testing with pilot holes. Remember this section here? The chisel point. It's a straight section, more or less perpendicular to the drill, and it's this section that's going to make first contact with the material. The problem is, it's not even a cutting edge. That's right, the chisel point doesn't cut. It just displaces material to the sides, to the cutting edges. That's why, when you're starting a hole, you need to push harder on the drill. You're not cutting yet, you're just displacing material. And if you're using a hand drill, there's a good chance you're fighting to keep the drill in the correct spot too. Even if you have a punch mark, if it's handheld, it'll have a tendency to walk. All of this is amplified when you use a larger drill, because inherently they have larger chisel points. Smaller drills are usually more manageable, but if you're drilling on a freshly painted panel, it doesn't matter. If you can't afford to do anything less than a perfect job, it'll inevitably walk. It's just the nature of the thing. So, pilot holes, sometimes referred to as pre-drilling. It's the little hole you drill first, smaller than your final size. You can have just that pilot hole and then go straight to the final drill, or if you're going for a big hole, do it incrementally. It all depends on how much material you're going to remove, and also how you're doing it. There's a difference if you're on a drill press or milling machine, or if you're doing it by hand. What you want is to make it easier for the drill, and the way to do that is by actually avoiding having the chisel point do any of the work. You just want the cutting edges touching the part. So the minimum size for a pilot hole is anything above the chisel point length. The central part of a drill, between the flutes, is called the web. It begins just after the shank and runs all the way down to the tip, where the cutting edges meet. Yep, the chisel point. Like I said earlier, the chisel point has a tough job. It compresses and deforms the material until it's pushed to the cutting edges. So the larger the drill is, the more you have to push until it starts cutting. What you might not know is that, after sharpening a few times, the chisel point actually grows in size. And that happens because the web tapers from the shank to the point. Rigidity and strength, that's why. And it's also a compromise. A thin needle penetrates much better, but it also bends easily. And a drill bit is not much different. The key point here is, as you sharpen, the drill gets shorter. The chisel point gets bigger, and the consequence of that, you need to apply more force to start drilling. If you don't have a pilot, of course. But there's a way to get around this problem. You thin the web. Web thinning is the process of removing material from the end of the point, in a way that the chisel point gets smaller and the web gets thinner. That helps drilling because, like the thin needle, there's less stress in the drilling process. Also, if the chisel point is smaller and symmetrical, the drill will behave better when it first touches the part. For comparison, here's what happens when a larger chisel point meets the part. The drill flexes and wanders for a while until it self-centers on the hole. If the chisel point was smaller, this wouldn't be so dramatic. So we can say a thinned web helps with centering. Now the problem with thinning the web on a cheap drill like this is that we're gonna have a weak chisel point. Here's two drills of the same size but different price, 11mm. Cheaper drills usually don't have a lot of material invested in the web, and that's probably why many of them are bent out of the box. So thinning this cheap drill is actually a bad idea, as it's gonna lose a lot of tip strength. Have these in mind, this is just for demonstration purposes. Did you hear that tick? I'm gonna play it again. That was the tip breaking. Like I said, it doesn't make sense to thin the web on a flimsy drill. And I might have exaggerated as well, so this was not unexpected. The 13mm did better, but my conclusion about web thinning is, don't do it. Just drill a pilot. The thing is, unless you have a lot of practice, you're never gonna get a perfectly symmetrical drill. It's not worth the fuss to do it by hand. But at least you know what it is when you find a drill with these two notches. In a point angles chapter, I mentioned a different type of grind common to find in cobalt drills. I meant the split point type. It's the one on the right. It's also a form of web thinning, so all the benefits are there. You have the typical flank of a conical grind and the cutting edge, but then a secondary relief is ground. That's done in the way that the point is split in half, creating two very small cutting edges. These two cutting edges are self-centering, and that allows you to do stuff like this. Stainless steel. Obviously, don't hold stuff with your hands. The point here is that split points self-center and are great to drill by hand. They're also very rigid because their web is usually very thick. I think it has to do with having more material to strengthen the chisel edge and provide better support for the split point. But over time, it's inevitable. The small cutting edges will wear, and when that happens, sharpening without a fixture won't be easy. I mean, you can do it, as I will try to do it, but you need a very sharp grinding wheel. This is really the downside of split points. You can turn them into conical points, but that's not really the best option. The chisel point will be huge. Sure, you can use pilot holes or thin the web, but you'll lose the best thing about split points, which is efficiency. Split points are made so you can work fast, without the need for pilots. But this works the other way around as well. Turning thin web drills into split points will not give you a long-lasting drill. But again, for demonstration purposes, hold the drill with the chisel edge in line with the corner of the wheel. Point up the drill at a slight angle to the left and start shaping the relief. When there's enough material removed, you'll get closer to the point. You have to be careful there, as you don't want to go overboard. Just split the point until the geometry is symmetrical. This is easier said than done, so be prepared to practice. These two drills were the first I've ever tried to split point by hand. I know they're not that good, but let's try them. Oh, one thing I didn't mention. Split points are usually ground on 135-degree points, but there are also 118 split points. The former should give you a point that lasts longer. I was being extra careful at the beginning, but the tip of the 13mm broke anyway. The 9.5 survived, probably because I removed less material, so the tip is a little bit stronger. Also, I didn't have to push as hard to drill the hole, but that's just because the drill is smaller. So, quick summary of what to use and when. For mild steel and other soft metals, avoid using very old bits. This one, from the beginning of the video. I believe this one is at least 50 years old. So yeah, replace with HSS. Trust me, this alone will make a huge difference. For stainless, use cobalt. Hardened steels, carbide. For holes larger than, say 10mm, take the time to drill a pilot hole first. It's a good practice that will help you save money. Big drills are not cheap. If you can't or don't want to drill a pilot, the conical point, when ground correctly, works really well. Plus, it's really easy to touch up on a bench grinder, so maintenance is guaranteed, cheap and quick. The downside is big holes. If you can, do them on a mill or drill press. If you have drill bits that were sharpened too many times and you absolutely must save them, try web thinning. Finally, if you do a lot of hand drilling, go for split points. They're the best for that. This is just a generalization to get you started. If you're drilling really big holes, you should look into hole saws and annular cutters, depending on what type of machine you're using to drill. But that's out of scope for this video. To finalize, I want to point out that web thinning and point splitting require practice to get good results. If you're sharpening by hand, it's likely that your first attempts will break, just like mine did. But since we're talking about first times, this might be the right time to let you in on something. This is the drill I sharpened at the beginning of the video, and believe it or not, it was only the third drill I've ever sharpened. And this was the first, 8-9 years ago. I wanted to modify this A-series timing plate to take duplex timing gears. Originally this was for single row, and in order to do that, these two holes need to be slightly bigger and countersunk. So there I was with my new fancy drill press. I had the drill, but the tip was dull. I also had another one at hand, so I tried to copy the business end. But now that I look at it, it's embarrassing. I can't understand how I ended up with the relief backwards. Now this was the time before I knew there were videos on YouTube where you can learn this kind of stuff. I don't think I even knew what a lathe or a mill were at the time. Anyway, I sharpened this drill a few times, but it still wouldn't cut. It just rubbed, obviously. And that meant two things for me. One, I added one more drill to my bed drills tray, and two, I convinced myself I wasn't able to sharpen drill bits. I just didn't have it. And from that moment, up until now, it never crossed my mind to try again. It's like I limited myself and now I just feel stupid about it. That's the reason why I made this video. I know there are many videos out there about drill sharpening, but one thing I keep seeing over and over in the comment section is people saying they tried, failed, and then got themselves a drill sharpener. And I don't want that to be me, because I just got these. Look, if I'm into machining, even if at a hobby level, I have to begin by learning the basics, like drill sharpening. No excuses. So the fact that my life just got easier with this machine actually made me learn how to sharpen by hand. And it's not that hard at all. You just need to have a good understanding of the geometry and then do it. I was really surprised when I had my second try a few days ago, and it was kind of successful. So after practicing for a while with that second drill, I managed to repeat the process for the third time. This time for the camera. And even if out of focus, sorry about that. But now you know. If you're like me and have a box with bed drills, give yourself a chance and try sharpening for a couple of hours. If my video doesn't help, watch some other videos from the usual suspects, but don't give up. And please, don't get into wooden or 3D printed jigs. You now should know how a drill looks like after sharpening. If you're looking for a quick and easy way to consistently sharpen drill bits to a good standard, this is the type of machine to get. Full disclosure, this was sent to me by Vevor, free of charge, with the agreement that I show it on the channel. It can do 3 to 13 mm, but if you want more, there's another version that can go up to 20 mm. That version is basically the same as this, only with 2 chucks and more collets. So to sharpen, the first step is to set the drill in the chuck. This sharpener requires the cutting edges parallel to the flats on the chuck, and of course some depth of cut. That's where this fixture on the left comes in. If the cutting edges aren't parallel to the flats, rotate the drill a little bit. Set it by eye. It does need to be perfect. Next, ensure you have the CBN wheel and not the STC. This machine comes with both. The CBN is for HSS and the STC, which is diamond, is for carbide. Set the desired point angle. Note that this hole was turned with an offset and produces an eccentric movement. That's to grind conical points. The relief is created as the backside of the drill gets closer to the wheel. Flip it and repeat. The finish looks really good. Although magnified, I reckon it might be a little bit coarse. But I don't think that will make any difference on the weight cuts. Wow, that's a clean hole. Unfortunately, I can't show you the 13 mm because I forgot to press record, so I don't have the footage. But it was more or less the same, although the drill does show more wear than the 9.5. I'm not sure if the bright spot is a leftover from the previous grind, the split point by hand, or if it's a witness mark from rubbing. When I was drilling, it did sound like it was rubbing, but was also cutting really well, so I don't know. We've seen what to do when it rubs, but I'm not gonna bother with that right now. Let's jump to the next point, web thinning. The cover says this spot is for point splitting, or point grinding, web thinning. That's what this does. Problem: do you see any? This is actually quite common. The machine will blow up the tip if it's not adjusted properly. Basically, it's grinding beyond center. So if you have one of these sharpeners and this happens to you, know that you can fix it. Set the pins to create the smallest relief possible, should be positions 4 and 5. Release the set screws on the web thinning fixture, and don't remove the plate. Instead, make the smallest adjustment you can. In this case, since we want more material in the center, we need to move the plate away from the wheel. Slide it towards the machine. And test by gently dropping the chuck all the way to the right. This should help you saving some drill length, as you can gradually increase the amount of grinding until it's just right. If you don't do this, you'll have to start by grinding a fresh conical point every time after you make an adjustment. Another tip for you. This adjustment is very, very sensitive, so you'll need some patience. And one of these do help a lot. Once you get the machine thinning the web all the way to the center, it's done. If you find the relief is too much, even with the pins in position 4 and 5, you can lift the whole fixture a little bit. Basically, this whole setup requires some experimenting, but once it's properly done, the results are very good. Doing web thinning on a fixture allows the machine to actually split a point. It's almost like a proper split point, only we don't get to have the back relief, as this model can't do facets. Again, very clean hole. However, the conical point was faster and I felt like it required less force. Well, both drills survived and don't seem to have significant wear. So, a moment ago I said this model can't do facets, and that's correct. But to be fair, the secondary relief on split points isn't actually a facet. By facet, I mean a face that's flat. I believe the back reliefs you see on split points are ground on big wheels. And as you know, big radius over short distances kinda produce something that looks flat. Anyway, the 13B is only able to thin the web. If you wanna do factory-like split points, you should look into the 13A. Looks like it's the same machine, but it's not. Instead of having this fixture on the front, the 13A has a different fixture. That's the fixture to grind split points. So what does this mean? With the 13A, you can't do web thinning, only split points. With the 13B, you can't do split points, only web thinning. You might find combo machines on the market that can do both, but those won't be from Vevor. Personally, I wanted the 13A, but somehow got confused and ordered the 13B by mistake. And this is why I want to make this clear for everybody. I know the 13B claims to make split points, and technically it does split the point, but that's not the split point we refer to when we talk about split point drills. So let's say I wanted to show you how split points are done. Let's also say for a minute this machine had that capability. I'd use the fixture on the back to grind the secondary relief and split the point. Something like this. Yeah, this last one grabbed a little bit at the end. It happens, especially with bent drills. So a little bit of wear in the 13, but the 9.5 looks good as new. And this is the difference I see right away between hand sharpening and using a machine. When I did the split point by hand, the tip broke immediately, despite how careful I was starting the hole. The same for the web thinning test, but with the machine grinds, I just didn't care, and they didn't break. Granted, I don't have much experience hand sharpening, and definitely could have done a better job. But I do believe the machine is just more convenient. Starts with consistency. You always get the same result. The angle you dialed in, the relief you set to be made, the finish of the wheel you have mounted, and more importantly, symmetrical features. At the end of the day, that's what you want from a drill bit. You want it sharp to make its job, a hole of some expected size. Now, the machine does have its limitations, the more evident being drill size. Realistically, you'll not be sharpening many drills below 5mm. The setup is kind of tricky and not worth the time, unless you have some special drill you really want to save. Above 5mm you're good, but only up to 13mm. Or 20 if you have the bucks to buy the MR-13B. That's why it's so important to still learn how to sharpen by hand. You won't find yourself limited. Another compromise is that you have to make a choice. Do you want to be able to make split points or web thinning? Also, just to clarify, this machine can't sharpen end mills, only drill bits. But unlike a quern or another tool and cutter grinder, where you need to spend a good amount of time in the setup, this sharpener is really fast. I mean, you can sharpen a drill bit in less than a minute, and that's included the setup and relief angles. So, should you buy this machine? I don't know. Do you have some drill bits to sharpen? Do the math. Let's consider the average cost of an HSS drill bit up to 13mm, $3. This machine is priced around $300. Do you have 100 drill bits to sharpen? Or how long will it take you to sharpen 100 times? Also, are your eyes still good? Mine aren't what they used to be, so I can appreciate sharpening without having to inspect every drill in detail. Okay, slight tangent on a health and safety subject. And this is not only applicable to this sharpener, but to any machine that produces grinding dust. There will be tiny metal particles in the air around you. If you're using a grinding stone, there will be some of that too. And none of that is good for you. So please use a respirator. Something like this. There are other brands, this is just an example, but make sure it's capable of filtering small particles. If you are using one of these machines, I recommend you check out the vacuum cleaner adapter designed by Functional Print Friday. It attaches to the exhaust part of the machine and allows you to use the vacuum cleaner to pull out some of those tiny particles. This doesn't mean you should ditch the respirator though. But while running, the vacuum cleaner does help. I must say it gets a bit noisy. I tried to redesign the adapter, increasing the port cross-section and reducing all corners, trying to help airflow. Yeah, it didn't work. But at least it's a direct fit for my hose without the need for adapters. So if your vacuum cleaner has a 2-inch hose connection, check out FPF's adapter. If you need the 32mm version, I'll make sure mine is available as well. Oh great, hold on. So the first rule of the Sharpening Club is, you do not talk about the Sharpening Club. The second rule of the Sharpening Club is, you do not talk about... Right, where was I? Family member. Just a couple of drill bits. Just a couple of 54 drill bits. If the word gets around, actually some of these are quite interesting. I know the big ones came from an old machinist back in the early 90s, but I think a few more probably came from the same place. Web thinned, nice 10mm drill with integrated pilot, long series. All of these seem to be for aluminum. Tight spirals, these are to drill and remove chips fast. Morse taper 2. This is not quite web thin, it's more like point relieved. A drill with 3 flutes. Anyway, I was asked to grind all the Morse taper 2 shanks to 10mm so they can be used in a cordless drill. I really don't want to do that, partly because I believe they're not going to be used, like they haven't been in the last 30 years, but also because it's a shame to modify them. They'll probably end up ruined. Plus, look how well this fits my late steel stock. So I think I'll ask to keep these, and of course, offer to replace them with new drills of the same size, but with the 10mm shanks. And that leads me to this chapter. So, how many of these do you have? You know, when a drill slips in the chuck and a burr like this is raised. I know some people don't care, and it's not every day that you have to use a drill in a collet, but I hate when that happens to me. And I can't just ignore it. That's why sometimes you see shanks with marks on my channel. What I usually do is grab a file and remove the burr. Typically by hand, but I might spin it on a lathe if it's too much damage. like these Morse tapers. I don't think it's worth regrinding them, so I'll remove the majority of the rest first. Then with a flat stone, I should be able to get rid of all the burrs. Later I'll check if they slip, but only after sharpening. Since I have here some good examples, I might as well show them. This is a standard drill, standard in terms of helix angle and general flute design. And this is a parabolic drill, I'm 90% sure. The difference is in the helix angle, which is higher, more turns for the same length, and the rolled off heel. The web is also thicker than standard. Not sure this is clear with this. I have bigger ones, let me try to show you. These are 10 mm. Higher helix angle, this is 33, maybe 34 degrees, the standard one is 28. Parabolic drills are ideal for deep holes where chip removal is critical, and they really excel in softer materials. I happen to know the person using these usually drills sheet metal, so I wonder if they're breaking because of that. They also have a tendency to screw in when you drill sheet metal, so that might be a factor as well. Anyway, just wanted to show you these differences. As for sharpening the flutes, or should I say the margins, that can be done even in a D-bit grinder if you have this attachment. But in practice, it's just not worth it. Why would you want an undersized drill? Even if you want it just for pilot holes or pre-rimming, the sharpening process takes a lot of time. It's not worth it, in my opinion. What's worth is showing you one last type of grind, the multifaceted type. If we go back and have a look at the carbide drills, we'll recognize the cutting edge, a secondary relief, and a third relief that also splits the point. What's different with these, besides having an extra relief, is that all these features are facets. They don't start as conical points like we have seen before. 4-facet drills also exist, but I don't have one to show you. Actually I do, spot drills. Obviously these are all ground on a machine, but if you're desperate, you can kinda replicate it by hand. Just know that this isn't what I'd call a beginner's type of grind. So, point angle, 135 or more. I started by grinding the point to the correct angle. What I was looking for was the final orientation of the cutting edges. Then, with the drill slightly angled to the left, in a way that the cutting edges were parallel to the axis of rotation, I started shaping the relief. For this part, you want to go high on the wheel. I also found it easier to grind the relief all the way to the cutting edges. It helps with checking if everything is symmetrical. Then I moved the drill down and repeated the process to create the cutting edges. A light kiss on the wheel, and that's it. More than that and it'll be too big. Start over if that happens. I've never seen this being done by hand and I recognize it's not the best way to do it. At least for carbide tooling, it certainly isn't. Don't even try. But like I said, if you're desperate and can't make a conical point cut, this does drill a hole. Maybe it's something to try out? Now the right way to grind the multifaceted point is with a machine. All the angles need to be known, correct and symmetrical. That's something only a machine can offer. And my D-bit grinder should be able to do it, so let's set it up. First set the fixture for the point angle, that's half of the included angle. Next set the relief angle. I'm setting it to 14 degrees here. Zero the dial and make sure the 180 position is clear. The cutting edges need to be horizontal, and that's something that looks easy until you realize it's not. A ruler can help, but might not be enough. Here's another tip. If the drill is too worn out, or if it's hand ground, like the ones I've been using in this video, do a cleanup pass first, and then set the cutting edges horizontal again. Make sure the drill is tight on the collet, and start grinding the relief facet. Once the relief is ground, tilt the fixture and set the angle for the cutting edges. Carefully grind the cutting edges until they meet at the center. If you have a train die, you'll notice the point angle is 118 degrees. Yeah, I got that wrong. I wanted 135 and only noticed when I was editing. What I also missed was the start of the 9.5 hole, which didn't go very well. The heel started to rub and I had to stop. You can't see the witness marks here. So I did what I've been preaching and ground an extra relief for the heel. The chisel point angle really gives it away. This shot isn't the best, almost looks like it's backwards, but that's just where. In reality, the measured angle is around 110, at best, so there's almost no clearance. And what caused these was not having the cutting edges perfectly horizontal when the drill was ground. So right after grinding, you can check the chisel point angle to verify whether the drill was oriented correctly or not. The hole looks clean, the drill looks good, no drama while I was drilling. Yeah, this went well despite the lack of clearance. But the 13 looks to have more clearance, so let's give it a shot. Again, no pilot hole. That didn't sound good at all. So this 13mm has been giving me problems the entire video. I remember the runout was visible when it first came out of the box, so I assumed the drill was bent and didn't care much if it ended up burnt after drilling a hole. Plus, with hand grinds, I wasn't sure if the problem was me. But it happened with the Vevor sharpener and now happened again with the D-bit grind. It was drilling fine, but near the finish it started to rub. A lot. By the way, when the margins cook like this, the right thing to do is cut off the damaged portion of the drill. But right now, I just want to understand why this went wrong. We know the 9.5 had a clearance issue, and although this one looked better, looks like it's not by much. The heel was rubbing as well. So that might have been the problem, or part of the problem. The other part might have to do with it not being straight. But instead of assuming, let's actually check. Just for reference, here's the runout on my grinder with the 13mm collet and the 13mm carbide drill. Let's call it 3/10. Now the HSS drill. 1000 on the shank, but if it's actually bent, the tip will be worse. So let's set the DTI there. And looks like this is the other part of the problem. Not so sure about the bending, looks more like a poor grinding job on the flutes. One of them has insufficient clearance. It's almost at the same height as the margin, and that margin is not as high as the other, so everything is uneven. Add that to the 4000s of runout on my drill chuck, yeah, it doesn't look good. So, as the hole gets deeper, there's more drill length in contact with the sides of the hole. That's why the problems with this drill only start happening after some depth. I could have selected better drills for this video, but in a way, I'm glad I didn't. It only goes to show you shouldn't buy the cheapest drill bits you can find, even if they look nice, with fancy colors and words on the box like titanium. But these days I don't buy this kind of crap anymore, and to be honest, I'm not spending that much more. I like cobalt drills. They're a little bit more expensive, but they're worth it if you drill mostly steel. I also like these ones. I buy them at Morgan's. They're good, slice pretty well. The thing with these drills is that most of them are split points. And since you watched this entire 1-hour video without skipping a chapter, now you know why this is a problem. You need to be or own a machine to resharpen them. It wouldn't surprise me if this was a date code. It probably isn't, but I know none of these Morse taper drills have seen the light of day since the early 90s. 20.5mm from Sadex. Sadex? Not sure if it's HSS. Might be high carbon. These two are definitely HSS. The 3 flute is 16mm and the last one is 15.7. And looks sharp too. The point angle also looks fine. I don't think I'll touch this one, other than stone the shank, of course. The 16, however, it needs more work. Clearly someone tried to use it in a regular chuck. I wonder how that went. So here's what I'm thinking. The Sadex and the 3 flute need to be resharpened. If I had the MR-13B sharpener, I could at least do the 20mm, but I don't. So the second option is to do it by hand. That's always an option, but I've been thinking. These are big drills considering the machines I have. My machines are small, not very rigid, and the motors are weak. So hand grinds will not help the case. I want a machine grind. Luckily, I have a third option, which is the multi-facet. I sharpened the 20.5 the exact same way as I did the 13mm, even down to the point angle. But as you know, in tooling, looks aren't everything, and there's only one way to find out if this is actually any good. But while we still have the D-bit grinder on the bench, let's have a look at the 3 flute. I have no idea what the point looked like when this was new, but right now this looks like a hand grind. The angle is too steep, less than 45 degrees per tooth, and the cutting edges and reliefs are just not consistent. But I don't think I'll make it worse, so let's do it. Reliefs first, and now the cutting edges. Like I said, I didn't know how the point of a 3 flute drill should look. I made a quick search, and it seems like this could be an option. But now, I think the cutting edges might be too long. If they were shorter, they should be stronger. Let me know what you think. $5mm, freshly sharpened. Right. So this happened. It's not the first time I'll style the lathe, but it was the first time while I was drilling. It's also my first time using a Morse taper drill. I was worried it was going to spin, so as soon as I felt the vibration, my immediate reaction was to feed harder. Kinda like when you're parting off and it starts to chatter. Your instinct might be to back off, but actually you need to do the opposite. Feed harder to get under that chatter. These if you have a machine that's rigid enough. The right tool, square to the job, on center, etc. This is not a parting off video, and I don't want to get into those details today, but I also don't want anyone to get hurt by just feeding harder without having the basics covered. I just wanted to explain why I had that reaction. Maintain high pressure to prevent spinning. Please be careful using machine tools. So, first impressions. The drill doesn't seem to have any damage. It doesn't even show signs of being used, except for the Morse taper section. That's a bit scored. The surface looks polished, but it wasn't really polished. So, I wonder if a light touch with 600 grit sandpaper could help. I'm not going to do that, at least yet, not until someone tells me that's a good idea, or to do something else to keep this from spinning. The hole looks okay. I mean, for a drilled hole. I've done worse. But what surprised me was to be on size. But I couldn't leave it like that, and at the end of the day I came back to drill another hole. This time with a late dog on the drill to make sure it wouldn't spin. I also had a better feel for it, so I didn't feed as hard, and the feedback was much better. There was also a vibration moment, but in general it was easier to drill. Less pressure needed, I just had to feed and let the drill do its job. Pretty happy with this drill. Between these two tests I tried the 3 flute. I can't find the words to describe how easy it was to drill. Much easier than, say, a normal 10mm drill. It called for high feed, although there was a moment the motor couldn't keep up, but man, that's a good drill. I'm very happy with these new drills. If you're comfortable drilling steel and think brass should be easier because it's softer, let me tell you, you're one step away from hurting yourself. I've chosen this round piece specifically to show this. Something with corners or in sheet form, it's even worse. It can cut you real bad. The problem with brass and other ductile metals is that they screw themselves into the work as the drill breaks through. The positive rake geometry of normal drill bits will facilitate that from the moment they catch an edge on the other side of the hole. To prevent this, we can modify our cutting edge rake angle from positive to neutral. That can easily be done with a file. Just a few strokes should be enough. The drill will still pull, but it will be completely different and much safer. So, let's tie up some loose ends. First of all, take everything you've seen in this video with a grain of salt. I'm not an expert in drill sharpening, and even though I tried to dig a little bit on the subject in these last 4 months, it still doesn't make me an expert. I'm just sharing what I learned. Feel free to correct me in the comments. The biggest result for me of this whole exercise is to be able to sharpen by hand. I really thought it was something difficult, but it really isn't. It doesn't even require a lot of practice, once you understand the geometry that makes a drill cut. The Vevor sharpener is great to get consistent results, also to sharpen in batches. If you decide to buy one, please pay attention to the models available. The MR-13A makes split points, the B web thinning. The G also does web thinning, but can sharpen up to 20mm. The D-bit grinder is even better, but it's way more expensive and you won't get a drill sharpened that fast. As for results of the drilled holes, I measure them, but I don't think it means anything. There's no way a scientific result can be obtained from this, especially using bad drills. But for the sake of it, here they are. If I wanted a hole on size with some accuracy, I'd be drilling undersize and then rimming, or using a boring bar if I didn't have the rimmer. Or even better, drilling, using a boring bar to straighten the hole, and then rimming. This is just to say that, while I measured the holes, I wasn't expecting any precision to be revealed. Finally, I'd like to thank Bambu Lab for providing an X1 carbon 3D printer for the channel. Having a modern printer that prints reliably and faster than my old printer will definitely improve my delivery. If you want any of the models shown in this video, I'll add links to the description. Like this little tool. I couldn't stand the rod knocking on my grinder anymore, and I remembered I had this single point dresser. It didn't totally fix the wheel, but it's much better now and will hold up until I make the proper tool. Okay, I think that's all for today. Thanks for watching this longer video. Now go out and go sharpen some drills.